I started on this project coming up on 15 years ago, and it was really because it was the first story that I had heard about hope in a long time. And growing up at the tail end of the Cold War, my vision of the future was pretty much Armageddon. And the idea that someone might think really far into the future just wasn't even heard of. And I heard this story that was actually told by Stuart Brand to Danny Hillis. And I heard Danny Hillis has presented here before, yes? Yeah. And Stuart, I guess, is coming. And the story was of New College, Oxford. And for those of you who haven't heard it, it's at least versions of it are true. But when the school was built in the 1300s, it was built with these huge oak beams over the main common area. And 500 years later, in the 1800s, when they were taking a look at these beams again, they realized they had become rotten and beetle infested, and they needed to replace them. But they also realized that you couldn't go buy trees like this anymore in Europe. And it wasn't until they spoke to the school forester who said, oh, well, we have the trees that you planted. And it turned out that in the 1300s, they also planted a grove of oak trees to be harvested 500 years later to replace these beams. And it was this kind of very simple long-term thinking where just putting some acorns in the ground could be leveraged over many hundreds of years that Stuart Brand and Danny Hillis were remarking that our civilization really wasn't doing that anymore. And so Danny Hillis, whose background was in supercomputers, had been paying attention to the very fast space for a very long time, but he had never had anyone ask him about the things that could be better if they were made slower. And one of the ideas that he had was to make a very slow millennial clock. And he told this idea to Stuart. He told this idea to several people, including Paul and Kevin Kelly and Brian Eno, people who became the founding board of the Long Now Foundation, and several others who pretty much ignored the idea. But this group started talking about what values there are in long-term thinking, and that if you're only paying attention to the fast, you miss the problems that can only be achieved if you look at it on a generational timescale. We are not going to solve the climate problem in 5 years. You are going to solve it in 50 to 100 years. You're not going to solve an educational problem that has a 20 to 30 year at least return on your investment just by the age of the children, unless you're looking at it generationally. So these are the types of problems that they started looking at. And so Danny Hillis had this idea of this clock, this 10,000-year clock that would be an icon to long-term thinking and get people's attention on it. And Stuart Brand thought, well, that'd be great if we get people's attention, but what do you do with that attention? And his idea was a library or a kind of information service. And it was Brian Eno who was in on this discussion as well, who heard all these ideas and brought up this name, this name of the Long Now. And he brought it up as a story from when he first moved to the United States from England, when he had gone from basically London to New York, and he realized that when people were in New York and they said now, they really meant the 5 minutes that you're in. And in London, they meant kind of the time that we were in. And so he coined this as the Long Now. And the foundation took on that name and really pushed it to be the 10,000 years of humanity that has lived up to now. And 10,000 years is chosen. It's kind of roughly the Anthropocene that we've all been living in. This is the amount of time that we've been affecting the environment a little bit more than the environment has been affecting us. And if we can look back that far, then we should be able to look forward that far and take some responsibility for it. And so what would you do differently if you started taking responsibility for the next 10,000 years? And it's not billions of years. It's not millions of years. Both of these time scales really dwarf the human experience. There's nothing that you can possibly do to make a difference on these time scales. So it's really this 10,000 years when the last ice age retreated, cities started being created, and this is the human time. And even at 25 years a generation, this is only 400 generations. So you can imagine a story would have to be told 400 times from one generation to the next to make it through this time scale. And in fact, some of the only things that we have that have survived on this time scale are human storytelling traditions. So when I was brought on in 1997, it was originally to build the first prototype of a 10,000-year all-mechanical clock with Danny Hillis. And since that time, I've been collecting precedents and lessons from history, as well as modern examples where people have been trying to create things that could last on this time scale, or have accidentally survived on this time scale. One of the most interesting ones that you often find right off the bat is this one, the Antikythera device. And this was a device that was found off of Antikythera, Greece, underwater in the Mediterranean. It was over 2,000 years old, and it had things in it like differential drivetrain, which predated any knowledge of a differential drivetrain by over 1,000 years in Europe. And it wasn't until very recently that they started doing X-rays of it, and they could start reading some of the other inscriptions and see some of the other gear ratios. And now several groups of hobbyists and enthusiasts have reconstructed the full working thing. And so it turns out it was an astronomical clock, or a kind of orrery or astronomical prediction device. So this one makes me feel very good, even if I fail to build the 10,000-year clock very well, that someone might reconstruct it and have a chance at understanding it. And it's another good example of why mechanics. If we were going to make an electrical clock, if you find it at the bottom of the ocean not working, it's very difficult to re-understand what electronics or silicon chips might have inside them. And the other reason, obviously, for mechanics is that we're trying to change the way people think about time, and we want something that is inspiring as an object. And electronic objects are kind of just thought of as magic. Another example that comes to a lot of people's minds on these timescales is obviously things like the pyramids as well as Stonehenge. These are interesting examples where they have achieved this kind of timescale. Certainly 4,500 years is on our timescale. They have had successes and failures in their design. We still have their basic pyramid-ness about them, but they were robbed of all the valuables inside within only like 50 to 100 years for most pyramids. They were actually robbed very soon. And the casing stones on the outside were taken about a millennia later or that's many millennia later, almost a millennia ago, for building mosques in Cairo. But it's an interesting, I think one of the most interesting things is that it shows this kind of ablative layer technique. We still have the pyramids, and another thing that we still have is the Taj Mahal. And one of the reasons we still have it is because when it was built, it was actually encrusted with jewels all the way through the halls. And when the British sacked it for the final time, they spent a long time prying those jewels out of the halls, and those are now the crown jewels. But they didn't destroy this building, which is likely. Many other buildings at the time were destroyed, but this one wasn't because of how much time they spent trying to pry all those jewels out of it. And so this notion of having a high-value thing that people can steal but don't take the value of the real thing itself is an interesting one for lasting for a really long time. The other way of building something that can last for a really long time is to take a really long time building it. This is the cathedral at Cologne, one of the oldest cathedrals. It was started in 1248 and sort of finished by about 1880, so 600-year construction time. By the time it was done, it had already passed over the chasm of kind of unfashionability, which is the most dangerous time, it turns out, for anything that wants to last for a long time. When it turns out that one generation after something is built, when it becomes unfashionable, that is the generation that destroys the thing. And we see it here in San Francisco with the Victorian houses. They were basically destroyed a generation after they were built to build those beautiful tilt-up concrete structures in the 50s and 60s. And now we prize the Victorians again. So trying to find a way to cross over that chasm of the next generation that finds it unfathomable. And obviously, the Gaudi Cathedral is well on its way. It's in about 125 years into its construction, and probably will take another 500 or so, but it has already crossed this. It's already a UNESCO site. And so it's now, but there was a time where it was not worked on, not funded, about a generation after it was started. Another interesting way to survive a long time is to be surprisingly useful. The Eiffel Tower, you can imagine if you tried to build a structure like the Eiffel Tower in Paris today. Parisians are not really big on change like that. But it was built as a temporary structure. And then it wasn't until, it just so happened that it was built at a time where right around the time it was supposed to be torn down, it also became amazingly useful for television, or for radio and then television signals. And the Parisians weren't about to tear that down. And so it got another breath of life for a few more years until eventually it became an icon, and now the icon of Paris. Another thing that we are always looking into is what are the materials that can last on this time scale. And I'm always surprised as I look through old museums and old places what types of materials do survive on a millennial time scale. This beam is at a cathedral in Ely, England, and is over 700 years old, and it's supporting a 8-story tall cupola over that cathedral. And it's a reminder to me that even some of the most ephemeral materials can last on our timescale. And in fact, in Japan, there are buildings that have been a single continuous building that's over 1,600 years old and is many stories tall. And so these are examples of how you might get something to survive by maintaining them. Obviously, the humidity and rainstorms of Japan or the fog of Ely, England are not really good preservation environments, but if the roof is kept good, they can actually survive. The other interesting example in Japan is this one. This is Issei Shrine. It's been rebuilt every 20 years in an exact replica of itself for at least 1,000 years, and some evidence is that versions of it have been doing that for over 2,000 years. And this is a very rare picture. This is when both of the temples are built at the same time. You can see the one on the bottom is new, and the one on the top is just starting to be deconstructed. And so they deconstruct and reconstruct one every 20 years. The next one will be finished in 2013, I believe. I haven't heard if any of the recent earthquakes and tsunamis damaged this site at all, but I don't believe it did. Getting into some modern examples of things that have to last for 10,000 years. This is the Yucca Mountain Nuclear Waste Repository, now closed. Paul, did you go on this trip? Were you? Oh, you missed that one. We went here. At this point, the only thing that's built on this is those blue access ramps, and they haven't finished all the places that would actually store nuclear waste. I suspect that people's feelings about storing nuclear waste at nuclear facilities is about to change, or is already changing after Fukushima. So sites like this may reopen. But we did visit, and an interesting thing about these sites is that they have done literally billions of dollars worth of materials research into concrete and metals that we're now using, and they published it all, which is very nice. A site that I just came back from 2 weeks ago is the 100,000-year nuclear waste repository in Onkalo, Finland. This one is an insanely ambitious project. They have now done all the underground excavation down to the yellow part of this and are about to start the blue and the green parts where the nuclear waste will actually be stored, and it's going to be stored in these big cast iron and copper containers that are about 10 feet long. But they're doing a lot of the same stuff that we did at our site for the 10,000-year clock. They did all the core samples to be sure the rock would be stable, and this is the entrance going in. And you'll also notice, you also recognize this when I show some of the stuff from our clock site, is that if you're doing underground construction that has to last for a really long time, these lines that you see are actually the half barrels where they carefully exploded the underground charges to make the space. But if you still see those, that means that they didn't overbreak the rock, and it will likely last for a really long time. If you don't see those, then that means they've put too much energy into the ground, and it will probably collapse pretty soon. A site that I was at just this last winter was the Svalbard International Seed Vault. This is a 1,000-year facility. It's on the island of Svalbard. That's the runway of Svalbard. It's the most northerly permanently inhabited site on the planet. It's a kind of a strange condominium country. It has a very odd treaty around it, but it's also, and actually those little things up on the hillside up on the right is a huge U.S. military intelligence base where they keep track of submarines and things like that in the North Sea. So any country's allowed to do anything there. It was one of the reasons they did put the seed vault there, and they built it underground as well. And the theme that you're obviously starting to see is that anybody that's trying to make something last for a very long time tends to build underground. The pyramids were an exception, but they kind of built their own mountain to put this stuff underground. Here at the seed vault, they were trying to keep temperatures very low, so they went north and built into permafrost. This is also another thing that I find at all the multi-millennial sites that are being built. This is a retrofitted pump. Usually they always think that they can control the water coming into these facilities, and so far they all find out just a few years later that they cannot. So one of the biggest lessons I've learned from visiting these places is that you have to assume that the water is going to get in. You get a choice as to where you can divert it, but you don't get a choice as to whether or not the water comes in. But the most interesting thing about this visit actually was this book. I was signing the visitor log, and I looked, a couple pages back, and it was Jimmy Carter, and then a couple pages back was Ban Ki-moon, and the idea that you would build something this ridiculous and weird and put it in this ridiculous and weird of a place as hard as you could make to get there. And people still come. And they really failed to build this around the visitor experience. They almost never let people in. We only got through this door because they happened to be doing some maintenance that day. Jimmy Carter didn't even get through. But this is what the seeds look like. And all those cardboard boxes that for the 1,000-year storage, those are from the USDA. All the other countries use the actually engineered to last a long time boxes. The last site that I'll show you was another one that we visited. Stuart Brand got us into this one when he was asked to give a talk at the Brigham Young University. I told him, don't accept the invitation unless they let us into the genealogical vault outside of Salt Lake City. And so after a lot of cajoling, they finally did. And this is the last picture they let me take. But the Mormon Church has this amazing 1,000-year facility for storing all their genealogical material. Again, not designed around a tour. They claim that they don't let people in because of blue gene lint, which is the most corrosive thing they find in all of their microfiche. But it's a pretty interesting facility, and they were very nice once we got there, and they even showed us all the blueprints. They didn't let us take anything away. But again, this facility has flooded 4 times in its, so far, about 40-year life into its 1,000-year life. So they have cut trenches to route the water out of it underneath the big nuclear bomb-proof doors. So they also learned this lesson. And then there's the counter lesson, which is the Buddha's Abamyan. And this is the one that there's kind of no solution for, but I always like to be reminded of it. Whenever you are building something that's going to last for a really long time, there are always people that want to tear it down. And these Buddhas, these giant Buddhas, were built I think about 400 years ago. I don't have a date on these, but the picture on the left is in 1963. The picture on the right is from 2003, after the Taliban spent weeks blasting them out of the mountainside. And so some of the conclusions that we came to basically are that you can make it remote. In fact, you should make it remote. Cities churn too fast. Water will get in. We get a choice as to where we want to divert it. Oxidization control, which I'll talk about a little bit more about, you got to keep things from rusting, basically, and I'll show you some of our solutions on that. Design it not only to be known forever, but also to be lost and then refound. Things that get lost are often some of the only reasons they survive is because they get lost. So the Dead Sea Scrolls are a good example of this. Make it difficult to disassemble. So effectively what we're going to do is we're going to build a ship in a bottle with a clock underground. Make the space big, the entrances and exits small, and then a big machine inside. The other one is you design the long-term institution, so the maintenance can go alongside of the object. And that's where the cathedral in Ely and the Japanese temples really have won, and even making something out of something as ephemeral as thatch and wood and rice paper has lasted for almost 2,000 years. And the last one is this ablative layer technique. I'm not exactly sure what to do with this one, but if we were to put a bunch of jewels on the outside of our facility, it would be an interesting test to see how long those stayed there. And when Danny started the clock project itself about how to design the actual mechanics, he started with these 5 principles. And I've found them to be an interesting set of principles for a lot of design projects, especially software design projects. So basically that it should with basic maintenance be able to last, but we are going to allow maintenance, but it shouldn't catastrophically fail. You shouldn't have to disassemble the whole thing in order to maintain it. The transparency so that people who find it can understand it, the evolvability so that things like calendar systems can evolve. We know that the calendar system's probably not going to, the current calendar system's probably not going to make it for the next 10,000 years. And scalability so that we could make small prototypes and scale them up. And so as I said, the first project that I came on to do was this first prototype. And I'll just show you one of the design problems that we solved while making it to give you an idea of the types of design problems you run into when you're building a 10,000-year clock. One of the parts of the clock we wanted to build would synchronize the clock to the sun on any sunny day. And this would keep the clock from drifting, and the clock has a pendulum to give it good day-to-day time. But to keep it from drifting over millennia, we wanted this kind of phase lock to a natural cycle. So we figured out a mechanism that could do that. That's fine. You focus some light on a piece of metal expands, and you've got a mechanical trigger for solar noon if you baffle the light, so it just comes in at solar noon. The problem is this. This is a picture of the sun shot at solar noon throughout the course of the year. Basically, that's maybe once every 2 weeks or so. And it's showing you what's called the analemma, which is the equation of time. This is the difference from solar time to absolute time based on where the Earth is in its orbit. So you have about a plus or minus 15-minute difference. So if you're trying to synchronize a pendulum that's keeping accurate day-to-day time to the sun, they're going to be off. And not only are they going to be off, but it turns out that the Earth is slowing its rotation by about a second a century, and its axes are wobbling about once every 26,000 years. So that 23-degree tilt is wobbling on a 26,000-year cycle. So all of that came together into one math equation, which then turned into this CAM, which is called the equation of time CAM that we put in the first prototype that rectifies solar time to absolute time and allows the clock to keep accurate time over the 10,000 years. And then, of course, we also had to add an extra digit to the date of the Gregorian calendar to read in 5 digits. So this clock was started in the year 2000. This prototype was finished literally at the end of 1999. We were machining parts for it that New Year's Eve night, and it rang for the first time then. It's now at the Science Museum in London. And since then, we've built several more prototypes, including this orrery, which is a planet tracker, basically. And this was a prototype just to see about the types of interfaces that we could use in the final clock. And it also does calculation in a different way. Those disks at the bottom are all binary mechanical adding plates. So instead of doing calculation the way normal clocks do with gears that have additive error every time they go around, that little bit of error is adding in, this is doing binary digital calculations, but with mechanics instead of voltage states. So now we're scaling up. Give you an idea of the scale of the mechanism we're now building. That's the little dude right there. But these are all the parts of the clock that are now under construction, as well as the site itself. One of the parts of the clock there in the middle is the chime generator. And working with Brian Eno and Danny Hillis, they came up with an algorithm to ring a series of 10 bells in a different sequence each day for 10,000 years. So each time you visit the clock, you would get a unique chime sequence. And so we're now building that at scale. These are 8-foot Geneva mechanisms that there'll be 20 of stacked on top of each other. One of the main engineering problems that Geneva wheel presented us with was this one, and that is that if you're going to make any mechanical object that has rotating parts last for even 100 years, the bearings are really the most difficult design challenge. And so even stainless steel bearings, if they just sit still for 10 or 15 years, will actually start micro-welding themselves shut. So when I started this project, there was a very new type of bearing that was the all ceramic bearings that were only being used in satellites. Now they're being used in roller blades. The upshot was taking as long as we have to do this project as now we can source them and put them in the clock. So we're using all ceramic bearings. Some are off the shelf like these. Some we're building in-house. We're buying the ceramic balls, but we're manufacturing the races themselves. And again, I'll just show you one of the big parts of the clock that we're working on. This is a design of the whole power system of the clock. And these big gears here that you see have just rolled off the machining facility, and this is how big they are. Not only are they really big stainless steel gears, but they're also, every single one of those teeth is actually three-dimensionally machined so that there's only rolling friction on that gear. So it will last on the time scale that we need it. The other thing that we're now doing is we're working on site in West Texas. This project is funded by Jeff Bezos of Amazon.com, and he had a site for us, which was a high desert site. It was very remote and still in the United States. And it's just north of a town called Van Horn in the Sierra Diablo range, almost in New Mexico, very close to Carlsbad, New Mexico. And we're now well on our way to getting to the part of the mountain where the clock will go. Basically, it's a horizontal tunnel that then meets up with a raise bore drill, same kind of drill they used in Chile to rescue the miners that was going down. But actually, the way they're normally used is you push a pilot down and then you pull a raise bore back up. And that's where most of the clock components will go, is in this raise bore space. But our problem in making the underground space is that not only do we want to make an underground space like most mining projects do, but we also want to make it smooth and three-dimensionally curved so it will last for a very long time, and we have to do things like cut staircases into it. And it turns out there is no method of underground construction that would support these kind of designs. And so we started looking at places like Carrara, Italy, where they're carving underground, not with explosives because they want to mine the marble out, but now with diamond-toothed belt saws. And originally, these saws were really expensive and very very slow even. But in recent years, they have become very fast. And so they're normally operated by a simple hydraulic system that just cuts them a straight cut through rock. But what we've done is we've built a triple articulated robot that has a range of about 32 feet, and the blade itself is 9 feet long, but we can alternate to even blades as long as 16 feet long. And it can cut, by doing an alternating pattern of cut, break, we can actually make fully three-dimensional underground spaces and staircases. So that was one cut that was done over the course of about an hour through 5 feet of concrete. The top layer is broken away. And then if you do that for about a year, you get 250 feet of spiral underground staircase cut into solid rock. And that machine is going to be going out to the site next month. So we'll get to see if it works or not. Yeah, it gets lowered down on a set of 30,000-pound hoists, so it can start cutting those spaces. So that's what I have on the clock project. It's literally very up to the minute on what we're doing now. But I just wanted to talk a little bit also about Stuart Brand's idea of what do you do with on the information side of this project. If you do all this stuff and people come to this 10,000-year monument, what do you do with that attention? And we realized very quickly that you have a platform dependence, and one of the first platform dependencies that you have, besides computers, becomes language. And this is a good example of that. This is the Festos disk. This is one of the oldest examples of block printing known to man, and has yet to be decoded. And often people think that you can easily put instructions into little pictograms and they'll last for a really long time. But if anyone's assembled an IKEA desk, you know that pictograms aren't really that helpful, that you'd rather have some good words. And so we started collecting as many languages as we could to write with a gallium ion beam into silicon and then cast into nickel so that you could get density on the order of digital storage, but with analog so that you could put it under a microscope and read it. And so one side of the disk has a bunch of kind of meta information about the languages, and then the other side of the disk has 13,500 pages of actual image data. So you put this under a microscope and you can read it, and it has a basic sketch of over 1,500 languages on it. One of these disks was launched on the European Space Agency's Rosetta mission, which lands on a comet, I think I have it written down here, in November of 2014. So another 2 more years. It was launched in 2004. And I will just end tonight with interesting reminder that came up recently in the news about old knowledge and why it's sometimes important. No matter how fast certain knowledge moves, in fact, some of that very fast knowledge can be the most dangerous, and you can ignore the long cycles at your own peril. This was a warning marker in Japan that reads, "High dwellings are the peace and harmony of our descendants. Remember the calamity of the great tsunamis. Do not build homes below this point." And there was a small village that was saved because it was above this point, but there was many below this point as well that had been built in the hundreds of years since this marker was put up. And it turns out this is not the only marker. There was markers throughout Japan that were variously ignored or not ignored, and basically at the peril of those people. Thank you very much.
Good. So we'll go ahead and take questions, and the way this works is you raise your hand and Xander calls on you, and to make things as simple as possible, he will repeat your question so it gets caught on the tape, and thus we don't have to worry about people trying to crawl over desks to get microphones to people. So other than that, I think you all know the question-answer protocol. It's usual and customary, no special features.
I'll answer the first 2 questions also. No, we don't know how much it's going to cost. No, we don't know when it's going to be done. Go.
What's the actual power source for the clock?
What's the actual power source for the clock? So the clock is powered by 2 things. Just like we use 2 things for the timing source, we also use 2 things for the power. And the basic power source is the temperature difference from day to night that's collected at the same place we do the solar synchronization event. And so, all that does, though, is it keeps the pendulum going, and it keeps the clock ticking, and it keeps the clock knowing when now effectively is. But it doesn't update any of the dials, it doesn't ring the chimes, any of those things. All of that is powered by the visitors that come see the clock. So they come, and the clock is actually not moving, and it's showing the time of the last visitor. The only thing that's moving is the pendulum and the escapement. And so they come and they wind it up to now, and then they can see the calendrics move, the planets move, the star field move, all those things, and then it stops when it gets to now.
Why don't you say a word about how it resets after it stops?
How do you mean?
You come on the clock after it hasn't run for a while.
Well, no, that's when you wind it. Yeah. So you wind it up to that point, and then it stops.
Any thought given to trying to establish an oral tradition that was working parallel with the clock?
So, yeah, have we thought about an oral tradition or starting an oral tradition that would tell the story of the clock? And yes, we have. Actually, Danny just finished a really kind of interesting story that could be the beginning of that. But we've also tried to plant the idea into other people's heads. And for those of you who are Neil Stephenson fans, if you've read Anathem, it's basically the story of the clock told on another world. The meme has gone out into a few books. He's probably the most popular author. But we have been, so far we've been spending more of our time on actually building it. But the idea is you build something, as audacious and ridiculous as possible, and hopefully people tell the stories. But we'll see.
In determining the location where the clock's going to be, do you account for the movement, like the tectonic plate?
Yeah, what did we take into account for the clock site, and did we take into account tectonic movement? Yeah, so we purchased a site in eastern Nevada that was a similar high desert site originally, but when Jeff Bezos came to us with this project, he also came to us with a site. It's actually more geologically stable than the site that we had purchased in eastern Nevada. There's probably sites that are more geologically stable even than West Texas. There are places like Australia, the Barrier Shield Wall in Canada. But certainly on the 10,000-year time scale, the Sierra Diablo is a very stable place geologically. Any other questions?
So how much of this is used for, let's say, construction in homes, or like, I guess in the old days with nuclear fallout shelters, etc.? I mean, we saw like nuclear waste disposal, but how about in terms of modern structures that can be used and inhabited?
You're asking how much technology transfer for long-term structures is being used for houses and things like that?
Yeah. I mean, when you were building this, did you use knowledge from from cases like nuclear fallout shelters, and is that knowledge being used for people that are constructing homes now that want those to last for a very, very, very long time?
Unfortunately, it's. I mean, I paid my way through school working in the construction industry, and what I found is that people are trying to find ways to build houses a lot faster, not to last longer. And there's certainly a few exceptions in materials to that. But then my training also in industrial design, again, it's a lot about product obsolescence, not about heirloom objects. It's not about issuing that Rolex at birth as the only watch you'll ever need. It's about how many watches can we sell you throughout your lifetime. And so no is the answer, is that there's not been a lot of technology transfer to the consumer markets for things that are going to last a very long time. The rare projects are the big government ones like Yucca Mountain and Oncalo, where they are going against the grain to do it.
You said that the bar source for the clock is the balance of temperature between the day and the night. Did you put the risk of a new glacial area into the account of this balance?
Yeah, and I would say that well, sorry, I'll repeat that. The question is did we account for the fact that you might have another ice age in the next 10,000 years? And the way you account for that is that you always make sure it's a differential device. It's not an absolute device. So even in Antarctica, there is a big temperature difference from day to night. It's just scaled way down further than, it's all cold to us, but actually there's deviations of 40 degrees from day to night. And so as long as you make your device so that it's relative and not absolute, if you were going to say that the device would only work at 90 degrees and 20 degrees Fahrenheit, then it wouldn't work. But if you make it relative, and so it's actually done with 2 tanks of air that don't even have to be that sealed, but they self-compensate for, they move the center point with them. by being not totally sealed, actually. So.
You've seen so many places around the planet. Or is there a particular one that you could picture being a good or a decent model to use for the Mars colonization?
Well, certainly, I mean, yeah. Is there a good place for a Mars colonization site of the places I've seen in the world? I'd say Svalbard is a really good place just because it's basically all science-based community. You can fly there. It's not like Antarctica, which is really expensive to work in, but it's pretty much the Antarctic environment. And there's already a research university there. And I assume the U.S. doesn't have a presence there because of their base. They have a very small presence at that radar base, but they have a much bigger presence for all their Arctic research in Thule, Greenland, I believe. And so, but that's normal people can't really fly into Thule, but you can actually just buy a ticket and go to Svalbard. So that would be a place to have a cheap base for very cold and dry temperatures. So.
Can you talk a little bit about the decision to build the clock rather than anything else?
Well, the project is why a clock? The project is about time and is to get people to think about time. We could have a conference. We could write white papers, we could build other objects, but obviously a clock is centered around time, and conferences and talking about things is very different than actually doing things. And when we do conferences, and we do have a speaking series on long-term thinking, but the moment you start designing the handle of where the person winds the clock, you're actually having to think, what are the hands of the people going to be like in 10,000 years, and what are their aesthetic motivations, and all of those things, which are very specific questions that you never get to if you're not physically building the object. So we decided on a physical object for that reason. Why a clock? It's the thing that speaks to time most. It's the thing that records time if it's built at the right time scale. So.
And can you talk a little bit about the scale? Why so big?
Yeah, why monument scale? Well, I guess we've already built a small prototype and it hasn't achieved the goal that we wanted. The point is to be mythic, right? So to get people to tell the stories. So you have to build it big enough to be mythic. And the idea is that you build it on an architectural scale and people can walk around inside it. And even if they don't go and visit it, they might still tell stories that it exists. So that's the main reason.
Two questions. Can you give us some more detail about how it gets the energy? And second, have you thought at the handle, whether it will worn out by people pulling it?
Yeah, so a little bit more about how the clock gets its energy and how the handle for winding doesn't get worn out. How the clock gets its energy, we have a research project going on down in Los Angeles right now with Danny Hillis's Applied Minds group, and actually Tasha McCauley, student here, is working with him on the solar collector device. We're going to make it into a bit of the aesthetic portion of it, at least, into a public design contest, and Tasha was working on that. So we have a few ideas on it. There's a way to make a thermal motor out of nitinol, so shape memory alloy types of metal that when they get hot, they contract really fast. So actually, if you take two wheels and you cant them to each other at an angle, and you string nitinol between those two wheels, and you focus sunlight on the top one, it's going to contract, and then those wheels turn towards the bottom, bringing the next wire into the sunlight, next one in the sunlight, next one. So you can actually make a pretty amazing motor like that out of nitinol. The problem with nitinol is that as a 10,000-year material is that it fails the test of transparency. When you arrive and the nitinol is broken, the wire, it's now working on a principle that is opposite of pretty much every other principle that you would normally assume metal would do, which is to get longer with heat. So it's made of nickel and titanium. It's a great material to last for a long time. No one has ever found the fatigue limit of nitinol doing its cycling as long as it's kept within its temperature range. So it's a really good one, and it's one that we've tested, but it fails that test. So now we're looking at basically these tanks of air that push air from one to the other that just move a piston back and forth of graphite. It's a big graphite piston, and that's ratcheting the weight up on the clock. So we're testing that one now. We'll see how that goes. Oh, and the handle is just made a fairly massive amount of 316 stainless steel. So it just shouldn't wear out, but we'll see.
In thinking about, like, in 10,000 years from now, the people that live in this clock will think of us as really ancient. Did you sort of think of, like, what are the values of our society today that you wanted to convey? Or just personally, what do you think is so important about or meaningful about our society right now?
So the question is, what did we want to convey to the people 10,000 years from now, and what is important to convey? Is that right? So there was some funny mechanical choices, and again, these are choices that you only have to make when you start physically building something, which is, for instance, should we build this in the metric or imperial measuring system? And we're building it all in the imperial measuring system. And what we decided on when we came to choices like this, and we're putting the Gregorian calendar on it, and we're things like that instead of trying to predict the future and say, well, everybody's going to be metric at some point. Actually, if you look back through time, there was base 6 cultures, there was base 2 cultures, there was base 8 cultures. Base 10 cultures are extremely rare and recent. So what we wanted to do is make the choices where we placed it in the time and by the people that built it as much as possible. And if you look at history and what historians are looking at, they often want to know about those people. And so, for instance, it's it's the work gangs graffiti on the backsides of the stones and the pyramids that are the most interesting things, often way more than the hieroglyphics of the pharaohs that were sending the official message into the future. So things about day-to-day life, I think, are probably the types of things people would love to know the most about. We haven't really put that much into the day-to-day life side of it, but we have things like the Rosetta Project, I think, will act as a key to any information that gets found. And so that's the hope, is that those types of things do. I'm not sure if I totally answered your question. Did we find, what are we trying to convey? I think that the main thing that we are trying to convey is that we cared about those people of the future. I mean, I think if we dug into this mountain and we found the clock already there, what would we wish it did? I mean, I think it would definitely tell us that those people cared about us. So.
As a person who thinks in such a long time scale, what does exponential mean to you? I mean, looking into the research in the past, and what is exponential to you?
What is exponential to me on this time scale? And I don't know, when I think about exponential growth and the singularity and things like that, one of the best stories that I'm reminded of was told to me by Will Wright, the game maker. And it was there was a time when this new handheld device came out, and people saw people operating this device in the corner of a cafe, and all wrapped into their own world with this handheld device, and then wrote a paper and wrote a news story about it, saying that this was going to be the end of civilization because people aren't going to talk to each other anymore, they're not going to communicate correctly, and this was the book. So this was a story from just after Gutenberg, when the first books were coming into the mainstream and people could afford books. And so I think we often always think that we are on the brink of massive change. And I think that humans adjust to change slower than the technology does, and I think that we will keep bringing it back down to our pace often. And the real question is when things really accelerate our abilities and or to grasp that change. And I think the tentacles into the atomic world are still extremely slow compared to the software world. And so things that will change the physical world will still lag way behind the things that are in the virtual world. But that's my take on it. Are we complete? Thank you very much.